Welcome to this contribution on the electrical resistivity and the high voltage breakdown strength of polyamides, polyesters, and PPS. The base polymers are used a lot in products for the E&E and electric vehicle markets. Polyamides are essentially subdivided in aliphatic polyamides, polyamide 6,6 and 6 as the most prominent examples, and aromatic polyamides as shown in the picture on the left. Polyesters is mainly PBT, and PPS is displayed in the picture on the right. Now, clearly, each of these base polymers have their own pros and cons in terms of mechanics, CTI, hydrolytic, and other types of stability and electrical properties. And here we will only consider the electrical properties. More precisely, in the first paragraph, we will talk about the resistivity of these products, how we measure it, and how the resistivity depends on external factors such as temperature, relative humidity. And then in the second paragraph on dielectric strength, we will couple the information about resistivity to discuss the dielectric strength topic. And we'll present the values for the strength of the different types of polymers. Okay, starting with the first paragraph. If you look at these particular polymers, polyamides, polyesters, PPS, it's clear that they are semi-crystalline. That means there is crystalline zones in these polymers, denoted by the blue blocks in the scheme shown. Those blocks are characterized by a melting point, but there is also a large amorphous phase that is characterized by a so-called glass transition temperature. If the temperature is below the glass transition temperature, lower than the glass transition temperature, the polymer responds in a glassy fashion. The amorphous phase is hard and glassy. If the temperature is higher than the glass transition temperature, you end up in the rubbery regime. And this is important for the electrical properties of the polymers too. That can be understood as follows. If you take a polymeric slab and you put electrodes to it, here that is done with these yellow bars, and you apply a voltage across these electrodes, there will be an electric field that couples to the charge carriers in the amorphous phase of your polymer. And you can imagine that if the polymer is glassy, these charge carriers can move through the polymer much less easily than when the polymer is in the rubbery state. So clearly, the conductivity or the currents will be higher in the rubbery state and lower in the glassy state at lower temperatures. That is displayed here in a typical measurement for polyamide 40, a PPA, aromatic polyamide. So what you see depicted here is the resistivity of the polymer as a function of the temperature at which you do the measurement. And what is indicated in that red vertical line is the glass transition temperature. So what you see is that below, at temperatures lower than the glass transition temperature, you have a high resistance, low current because of the glassy response. The charge carriers cannot easily move through the material, and at higher temperatures above the glass transition temperature, you see a drop in resistivity because now the charge carriers can move through the material more easily. All this simply to illustrate that resistivity is indeed a function of temperature for these polymers. Now, for the case of polyamides, such as PPAs, but it goes also for all the other polyamides, the resistivity is also a function of the relative humidity of your local environment. And this is related to the fact that water is taken up by these polymers. It acts as a plasticizer, and it tends to lower the glass transition temperature of the polymers. And therefore, it affects this transition from a, let's say, glassy electrical response to a rubbery electrical response. Maybe more precisely, what you see in the picture on the left is the dry PPA has a glass transition temperature at around 120. You see that if the polymer picks up water at 85% relative humidity, TG drops to around 40 degrees Celsius, and therefore this transition from glassy electrical response to rubbery electrical response is now shifted. So clearly what you see from these pictures is that resistivity is also a strong function of the relative humidity. So temperature and relative humidity. This is a scheme of how we measure the resistivity of a polymer. It is done via dielectric spectroscopy. Maybe it is useful if I briefly point to here. This is the polymeric slab, and attached to that polymeric slab you have electrodes, and then what you do is you apply a voltage to that polymeric slab via the electrodes, and you pick up the current. This will be a resistive current leading to the resistivity of the material. There will also be a capacitive current, but we do not discuss that here. Now, what I want to tell here is that we can apply that voltage at various frequencies. So we can go to very low frequency, consider a quasi-DC situation, but we can also go to very high frequencies into the megahertz or even gigahertz regime. This is important because what we want to explain here very briefly is that the resistivity of the polymer does not only depend on temperature and relative humidity, but it also depends on the frequency of the voltage that you do apply. It's easiest understood as follows. Basically, in a polymer, there is charge carriers, such as ions that may stem from the flame retardant that you feed to the polymer or from the stabilizers that you feed to the polymer. But there is also chemical bonds that carry charge. So basically the chemical bonds that constitute the molecules. If you apply a voltage, there will be, basically these bonds get polarized and they orient. And if you apply a voltage of a higher frequency, they get polarized more often per second. So effectively, these bonds then carry more current, and therefore the resistivity of the material tends to be lower. Or if you want to have that displayed graphically, you look at the picture on the right. This is for a PBT, and there you see that at very low frequencies, close to DC, resistivity tends to be high because the bonds get polarized not very often, so there's not much current flowing. And if you raise the frequency to AC, then 50 Hertz AC, then you see that the resistivity comes down because there's now more current flowing through your material because you polarize the bonds more often. So in conclusion, the resistivity of a polymer depends on temperature, relative humidity, and on the frequency of the applied voltage. And this now brings me to the second paragraph on the dielectric breakdown strength of the polyamide PBT and PPS. Let me first briefly explain how we measure it, and then we try to connect this information to previous paragraph on resistivity. So here you see typical setup. On the left, you see two hemispherical electrodes with a diameter of 20 millimeters, which is typical. We have other electrodes too. And then in between these electrodes, and that is not shown here, you place a plate or a plate of your material under test. Typical thickness is 1 millimeter, but yeah, you can basically put in whatever you like. And then this whole setup is immersed in oil to avoid air breakdown near the electrodes here. And then you apply your AC or DC voltage, and you raise the voltage till the sample breaks down. Breakdown means till the sample conducts a current more than 1 milliamp. And then the outcome of this test is your breakdown voltage or electric field in kilovolts per millimeter of plate thickness. Now, here you see the typical outcome in the center of the slide for polyamide 6,6. So you see breakdown voltage in kilovolts per millimeter displayed on the y-axis versus temperature. And what you see is that there's again a transition towards lower breakdown voltages at higher at temperatures above the glass transition temperature. So when the material ends up, the amorphous phase of the material ends up in the rubbery state. Now, clearly, it's a question to ask, why does this occur? And I think it would also be very useful to know the lower limits of that strength, such that you can use your material in engineering applications and accommodate for the lowest, the weakest strength in engineering applications. So to pose the question more precisely, what we basically looked at is whether these drops in resistivity that we just discussed in the previous paragraphs displayed on the left, can those be responsible for the drop in the breakdown strength as displayed on the right? That was the precise question we tried to answer. And we did that via a COMSOL thermal modeling calculation. What you see in this picture is a part of an electrode and another electrode, and then you see a plate of polymer in between, 1 millimeter thickness. And to the polymer plate was assigned a specific resistivity. For the calculation on the left, it was 10 to the power 9 ohms times centimeter. For the calculation on the right, it was 10 to the power 7 ohms times centimeter, a value that you can encounter for a polyamide at temperatures above the glass transition temperature. Now, because of that finite resistance, there is a current flowing in between these electrodes here, and that may then lead to a resistive heating or a heat up of your material. And if the current is high enough, it can lead to a thermal runaway and a local breakdown. And what you indeed see is that if the resistance is lower, there's a big temperature increase leading to degradation and destruction of the material, a breakdown. If the resistance is high enough, so above 10 to the power 9 ohms times centimeter, that heat up does not occur and you're essentially in a safe zone. So indeed, if the resistance drops below 10 to the power 9 ohms times centimeter, these thermal breakdowns do occur. Now, having established that the resistance, the resistivity of the material is responsible for the breakdown of the material at high enough temperatures above the TG, one would like to know the, let's say, lower limit of the breakdown strength of such a material. And for that, we looked at wet material, wet polyamide 6,6, for which the resistivity is lowest. That is basically indicated in the dotted line in this particular picture. The full line is for dry material, the dotted line is for wet material. And what you see is if you have conditioned your material in at 85% relative humidity, so now it's in the fully wetted state, then at high enough temperatures, your breakdown field moves to 2.8 kilovolts per millimeter. So that is basically the lowest strength you can encounter for a polyamide, and that is the type of value you can use in your high voltage engineering applications. Now, just to be certain, we also looked at that in DC. So the previous picture was for 50 Hertz AC. That is reproduced here in the red line. We also looked at DC, that is the black line, and then you see that you more or less have the same strength values. So again, it is above, in this particular case, lowest value is 3.6 kilovolts per millimeter. So in other words, as long as you stay above 2.8 kilovolts per millimeter, you can use this material in your applications. Now, before we move to the conclusions, there is 2 more slides to show. This one is on PBT. On the left, you see the resistivity versus temperature of a PBT. And what you see is that, again, above the glass transition temperature is a drop in resistivity because you're dealing now with a rubbery phase. Charge carriers can move through more easily, but in all cases, the resistivity is above this level of 10 to the power 9 ohms times centimeter. Therefore, there is no risk, as was shown with these thermal calculations, for a drop in breakdown strength, and that is indeed what is shown in the picture in the experimental data on the right. You see that the breakdown strength is guaranteed, is high at all temperatures that we looked at, well into the rubbery regime, so up to 150 degrees Celsius. Now, for PPS, the situation is perfectly analogous as to the PBT case. Also there is a drop in resistivity above the glass transition temperature of your PPS, but the values never hit this, let's say, critical value of 10 to the power 9 ohms times centimeter. So also there, the breakdown strength, as shown in the picture on the right, is guaranteed for all temperatures. Now, this brings me to the concluding slide. What we have shown is that for PBT and PPS, there is very consistent, robust electrical performance, and it is really irrespective of the environmental conditions used. For polyamide, it's also clear, and that goes for all polyamides, that there is drops in electrical properties and breakdown strength above the glass transition temperature, but we have characterized the, let's say, lower strength limit very carefully, and they are very well understood. And therefore, if you choose to use polyamides in your high voltage engineering applications, maybe because of the superior mechanical properties of these products, you can use these data to guide your high voltage engineering designs. Now, this is basically what I wanted to tell you. So let me just show you our contact details. If questions do pop up as a consequence of this presentation, please do feel free to contact us.